we'll move on to the physics passage, right? And it's, if you go back to the Google Drive, it will be the second link. And this one's much shorter, I think, so more straightforward. So hopefully the passage at least is easier to read. Okay, so this is a really interesting question. I really like this question, so because it makes some very interesting parallels between different topics. So, okay. So I'm gonna show the result. Okay, so the answer is actually A. And immediately when you see words like parallel, series, you should immediately think of circuits, right? But that's weird. Why, when we're talking about things like flow and capillaries, why are we talking about circuits? Well, if you draw a capillary bed, it looks like this, kind of. Not a great artist, but looks kind of like this. And there's like millions of these like little tubes that kind of like break off, right? Each of these is like its own capillary and like bunch of tubes, right? But you get the point. Well, what is a parallel circuit look like? Well, parallel circuit, if drawn very simply, looks like this. Right? You guys see how it looks almost exactly the same, right? And remember that a series circuit is just a line, right? Or it's like it's just a straight line. So capillaries are very similar to parallel circuits. So A or B would be the correct answer. It wouldn't be C or D, right? Because they're not arranged in series. So remember that, and I'll close this and I'll open this. So remember that for the total resistance in a parallel circuit, this is the formula. And then for a series circuit, the total resistance is equal to this. Well, if we were going based off just regular series rules, you would just add them up, add up the resistances of each one, and then that would be the total, right? And that would give you like a pretty high resistance. But they said, why a network of capillaries is lower than would otherwise be expected? Well, because you're using actually the left formula, right? And that actually makes you have a smaller, total resistance compared to if you were wired in series. And again, remember the main thing about series versus parallel circuits is parallel circuits have many different paths to follow, just like capillaries have many different paths for blood to follow, right? And that's what makes it a parallel circuit, right? So that would be A. As for B, it could also maybe be that because it's also arranged parallel, but it doesn't really increase the total distance which blood must travel, right? And that doesn't really have a big effect on the actual resistance. The resistance is affected by it just being in parallel in general, and because of the nature of being parallel, you're going into different paths, right? If, for example, you took a series circuit and you made it really, really long, so to the point where you're the distance is the same as a parallel circuit, the resistance would still be smaller in the parallel circuit, right? Compared to the series circuit, even though the distance is the same for the blood to travel. Okay, that makes sense. All right, no other questions, please take a couple minutes to look at this problem. All right, so the correct answer is actually D, increasing hematocrit. So this actually really didn't involve that much thinking. This actually was just based solely on the passage, honestly, because they gave you the equation for Reynolds number, right, RE, and it's density, viscosity, velocity, and diameter, which is basically the same thing as radius. And said if the Reynolds number becomes too high, so if RE goes up, a fluid is more likely to become turbulent from laminar, right? And that's which of these is least likely to result in going laminar to turbulent? Which of these is least likely to increase Reynolds number, right? Which of these will not increase RE? Well, decreasing the viscosity is over here. If you make the denominator smaller, it'll make the whole number bigger, right? Because if you're decreasing the velocity or just decreasing the denominator, it'll obviously make the end result bigger. So it's not this. increasing blood velocity, well, velocity is on the numerator. Increasing something on the numerator will make the number bigger, so not B. C, increasing blood vessel radius. Radius is essentially diameter. So increasing diameter, again, in the numerator, increasing diameter will make Reynolds number bigger, so it's not C. Hematocrit, you kind of had to know it, but really you could do it from process elimination. Hematocrit is a protein that's found in blood, right? And it says the viscosity of blood is largely determined by the cell protein contents of blood, right? So increasing the hematocrit would kind of increase the viscosity, right? And if viscosity is increased, then the denominator gets bigger, the whole number gets actually smaller. So it would not really increase Reynolds number, which would not have laminar turbulent transition. It's because that D is right. Nathan, take some time for this question. So the correct answer is actually C. And for this, yeah, okay, so I'll go back to the passage just to highlight something. So the most important thing that you should have gotten is C is the compliance. At low pressures, veins have a greater compliance than arteries, right? And it tells you why, but not important. At high pressures above 20, compliance becomes nearly equal between veins and arteries, right? So at low pressure, veins have bigger compliance. When you get to high pressure, they have the same compliance. Keep that in mind. Now, like I mentioned, what is compliance? Well, compliance is delta V over delta B, and V should be delta, right? And in this graph, what is delta V? So if you notice, the y-axis is V, the x-axis is P. So compliance is actually just the slope of each line, right? And what it said was the compliance of a vein is high at low pressure, so it should be a very steep slope. And then it lowers out when you get to higher pressure, lowers out and becomes the same as an artery. So let's say arteries are like this, and we'll pretend this like the same line right here, right? So it looks something like this, which goes along with C. Let's look at the other graphs first, right? So this one is just one line, right? So this says just arteries have a higher compliance than veins at all points, right? Because their slope is always steeper than veins at all pressures, which is not the case. It's actually the opposite, and then it evens out. But this is wrong because this graph shows arteries having a higher compliance than veins at all pressures, all x values. So not A. B. Well, compliance doesn't actually. So again, I mentioned compliance is slope. Well, arteries have a negative. Here, this is a negative slope. So it never mentioned that they have a negative compliance, right? They have maybe a lower compliance, but that doesn't mean negative, right? So because it doesn't have a negative compliance, B is out because there should not be any decreasing anywhere or going down. As for D, so D has it might seem like the right answer at first because look at high pressure they actually even out in terms of physically they even out. However, if you notice, like I mentioned, compliance is the slope. The slope over here is very small, very, very, very small. The slope here is just constant, whatever, right? Very small is not the same as just constantly increasing at a good rate, right? So the compliance itself, the slope itself is not equal, right? The y values, the pressure or the relative volume actually might be equal at the end, but the actual slope of the compliance, which is what we're looking for, is not equal. However, with C, if you notice above 20, which is about here, this slope, they're relatively similar, right? They're increasing at about the same pace. They're almost like parallel lines at that point. Not exactly, but it did mention they become more equal, right? Not 100%, but it's close enough and it's the closest that we have. Whereas initially veins have a much higher compliance at low pressures, right? And that's represented by arteries having a very small slope, whereas veins have a very big slope here in the beginning that evens out. Does that make sense? If not, then please get started. So the correct answer is actually A. And I think the main thing to note in this problem is, again, reading the problem and being very careful with the wording. So what is it asking for? So person, they're measuring at the shoulder and at the wrist. And so 2 different spots. And then they had them raise the arm straight up and then hold it straight down. And then they measured the difference in pressure between the wrist and the shoulder in both positions, right? So they want to know the difference between the differences, if that makes sense. So the difference between the head and shoulder measurements is delta P, right? It's the difference between the wrist and the shoulder in one position. So the difference between the head and wrist when it's up versus the difference between these two when it's down. And again, I think Jack West had a really good diagram to explain this, right here. So they want this difference versus this difference, not the difference between the shoulder and the wrist, the difference between the difference, right? If that kind of makes sense, right? So this delta P, right, versus so delta PU, which I'll say is when you're going up, and delta P versus delta PD, which is when your arm is down, right? So there is now a delta P, but there's also, I guess, if you want to think of it, a delta P. Right? And the delta P is what they're asking for in this question, right? And the difference between these two differences should be equal in both positions, right? And you can see that here. What is delta P equal to? Delta P up. Delta P up is equal to
rho GH, or?
Yeah, exactly. Rho GH. Well, rho G delta H, actually. Because remember, height is relative. Everything is, we can set a 0 really anywhere. Rho G delta H, right? And it's written here as well. And rho is whatever the blood density is. We don't care. It's the same no matter which position your hand's in, which part of the body you're in, the density of the blood is the same. We're assuming G is also the same. Doesn't matter if your hand's up here. If you're looking at the shoulder, the wrist, G is always the same. So these two don't really matter. We're only really looking at delta H. Well, if your hand is raised, the distance between your shoulder and your wrist is, say, in here they use 60 centimeters, right? That's the length of your arm. Well, if your hand is down here, the difference between your shoulder and your wrist is still 6 centimeters because that's the length of your arm. The length of your arm doesn't change if you're doing this or this. Your arm is still the same length, right? So delta P D, which is when your hand is down, is also equal to rho, which we mentioned. Rho is the same no matter what. Rho is always the same. G, again, always the same. And delta H. Delta H is just the length of your arm. Again, length of your arm doesn't change if you're doing this or if you're doing this. So the delta H's are the same. So we can just cancel that out too. And you're just left with delta P when your arm is going up is the same as delta P when your arm is going down, right? It's that simple. Now let's go over why the other choices are wrong, okay? Greater when the arm is held in the air due to greater fluid potential energy. You may get confused by thinking, well, if you're putting it higher up, you have more potential energy because that's usually how it works, but that doesn't really make sense with kind of the pressure differences, especially with like potential energy. It's doesn't really make sense. So I can't really explain it too well because they're not related concepts in a way. So it's kind of really hard to explain. But if you were to increase like the height, it doesn't matter. It's just the height difference between your shoulder and your wrist, if that makes sense, not the actual like total height, because otherwise it would matter if you're standing on the first floor of a building or on like the 10th floor of a building. Your blood would be completely different and like it would be your blood pressure would be completely out of whack depending on which floor of a building you were on. If you were living in a city that was on sea level versus a little bit above sea level or below sea level. So we never really like look at actual height. We look at relative height. If that makes sense. Greater when the arm is held in the air due to increased height. Again, that's the same thing. It's the same logic. It doesn't work because we use relative height, not absolute height. Otherwise, if you were standing on the 10th floor of a building, your blood would have insane pressure and it would just burst or whatever. Whereas if you were standing on the first floor of a building, your blood would be like pouring out or something because it has no pressure. Right, so we use relative, not absolute. And the lower when the arm is held in the air due to reduced hydrostatic pressure. Again, hydrostatic pressure is kind of the pressure that's inside your body, right? Near your vessels. That doesn't change depending on the height either, because it's your hydrostatic pressure is very heavily controlled by things like proteins, by like just your everything in your body is just controlling the hydrostatic pressure around your veins, so it doesn't really change with height. So it wouldn't be D either.